Hello everyone. In this video, we are going to discuss an important limitation of Ampere's circuital law and how James Maxwell resolved it by introducing the concept of displacement current density. We know that the Ampere's law works perfectly for steady or static currents, but when the fields vary with time, a contradiction arises. In this session, we will see or understand that inconsistency, the need for the displacement current density, and finally we derive the modified Maxwell equation for time varying fields. Let's start with the Ampere's law. The Ampere circuital law in differential form is given by del cross H equal to J. Now let's apply the divergence on both sides. Now del dot of del cross H equal to del dot J. We know that divergence of curl is 0 for any vector. Therefore, del dot J here, because this becomes 0, del dot J should be equal to 0. But from the continuity equation, that is the continuity of current equation, it is clear that del dot J is equal to minus tau by tau T of rho v. And for static fields, since rho v will not vary with respect to time, so this will be equal to 0, and therefore the above condition that del dot J equal to 0 is true for the static fields. But in the case of time varying fields, this dou by dou T of rho v is not equal to 0. Therefore, you observe that del dot of del cross H is not equal to 0. But divergence of curl for any vector should be equal to 0. So this is what the contradiction appears in the Ampere's law. And this contradiction is called the inconsistency of Ampere's law. Therefore, to avoid this contradiction, Maxwell modified the Ampere's law by adding one more current density term called displacement current density, represented here as JD. Now again applying the divergence on both sides, del dot of del cross H equal to del dot of J plus JD. And as usual, on the left hand side, divergence of curl for any vector is 0, so I made it 0. And here we observe that del dot J, that is replaced by minus dou by dou T of rho v from the continuity equation. Therefore, del dot JD is taking a form time rate of change of the charge density rho v. From the Gauss law, del dot D is rho v. Therefore, in place of rho v, we are replacing with del dot D. Properly arranging, del dot JD can be written as del dot of dou D by dou T. And this JD here is equal to dou D by dou T by comparing the above. And this is called as a displacement current density. Substituting this into the Ampere's law, we get the modified Maxwell equation for the time varying fields. That is del cross H equal to J plus JD, that is equal to J plus dou D by dou T. This is also called as the Ampere-Maxwell's law. Now, the question is, why it is called as the displacement current density? It is called the displacement current density because no actual movement of free charges takes place, unlike the conduction current. It rises due to the time variation of electric flux density or electric displacement vector D. So even though electrons are not physically crossing the region, the changing electric field behaves like a current and produces a magnetic field. And therefore, this can be represented like this. Now, if we can properly explain this displacement current density, the best example is a charging capacitor. When a capacitor is connected to a battery, the conduction current flows through the wires. But between the capacitor plates, there is an insulating dielectric, so no actual conduction current flows. Still, the electric field between the plates changes with time, producing the displacement current. Thus, the magnetic field around the wire remains constant because the conduction current will be equal to the displacement current. And here, in this video, we understood that the inconsistency of Ampere's law, the concept of displacement current density, and how Maxwell modified the equation for time variables. This concept has played a major role in the development of electromagnetic wave theory. Thank you for watching.